All right, new unit time. We are starting on our last unit for first year chemistry. I know you're so sad because you're like, I just want more and more chemistry. There cannot be enough chemistry. This last unit is a little different. It's not as mathematical. With gas laws, a lot of math. Some of you love that, and it's just like, yeah, I can just do math and figure it out. This one, there's little tiny bits of math, but it's mostly conceptual kind of stuff. We're hitting two chapters. A little bit in each chapter. We're basically kind of hitting the important things for first year chem in both chapters, chapters 17 and 18. We're going to hit 18 a little bit first, and then we're going to circle back and hit some in chapter 17. But it's basically the idea of energy and reaction rates and how those things are related, and getting energy, putting energy in or out, getting energy out of a reaction. How do we speed up a reaction? What's the real process of a reaction, right? So one of the things I really like is you're in chemistry and stuff longer, is you look at the same idea from different vantage points, right? So we looked at reaction rates from, just law of conservation of mass, like, stoichiometry. Well, like how much of this chemical and how much of this chemical. Then we looked at reaction rates for types of reactions. Well, this is like single replacement, double replacement kind of stuff. We looked at reactions from a, what else did we do? Balancing reactions and that kind of stuff. Now we're going to look at them from like a rates point of view. You get into higher levels of chemistry, and there's other ways we can look at them too, right? So we're going to look at how do we speed up and slow down reactions, and we can learn a lot about how they happen in that route, right? So anyway, you should, because it's not so much so mathematical, you should do the thing where you crack the spine on the book if you have a physical copy of the book, or download the PDF, which is very unsatisfying. I don't know how so many of you are okay with just doing that. But anyway, we'll put a PDF up of the chapter 17, 18 stuff. The rate stuff is more 18. The energy stuff is more 17. So anyway, to understand reaction rates very well, we have to understand the way in which chemicals react with each other. Not just that this reacts with this, or this much of this and this much of, but physically what happens when we go from these chemicals to these new chemicals, right? And the theory behind how that happens is called collision theory, right? So collision theory is the idea behind how reactions happen. So you're going to want to memorize collision theory. Nice thing is, it's not very hard. I bet you can guess something about collision theory. Is there one thing about collision theory you could tell me? I bet you could tell me that in order to react, molecules have to collide, right? So collision theory, they have to collide. They have to hit each other, right? So thinking bumper cars, right? Bumper cars, not a whole lot of fun if you're just like, remember, don't bump anybody in your bumper cars, right? They have to bump into each other in order to react. That's one of the reasons we do a lot of our reactions in chemistry dissolved in water, right? Because they move around, right? Remember we talked about that with ionic things dissolving in water, so the charges are mobile. If I take two solid things and put them next to each other, those things don't collide very much, right? Because the molecule is just sitting there vibrating a little bit. So we've got to dissolve them in a little bit of water. You might remember back to a lab we did where we took copper, and it was a copper compound, I think it was copper sulfate, and put it on aluminum foil. And then you had to add a catalyst of salt, and then you had to add a couple drops of water to really get it to react, because you needed them to move around a little bit and stuff, right? So molecules have to collide in order to react. Another thing they have to do, so there's a picture of that because you didn't know what collide means, so I put a picture of collide on there. Another thing that has to happen is they have to have proper orientation. They need to be lined up correctly, right? So I think this is a great example for that. Can you see my pen? My pen here, right? So I have a pen and a cap. So if I want to go do this magical reaction where I go from a pen and a cap to a capped pen, what do I have to do? Oh, collision theory says they have to collide. All right, here they go. They're colliding. Are they? Ooh, it's not working. Why is it not working? Right? Well, it's not. They have to be lined up correctly, right? So in biochem in college, we talked a lot about enzymes, and they talked about a lock and key model. We've actually replaced that with an induced fit model, but a lock and key model I think kind of works well too. You have to line things up correctly. So a thing that enzymes will do is they'll help line things up correctly, right? So they have to be lined up properly. Now, we do a lot of arts and crafts chemistry with this unit, and I'll have students draw pictures of the collision theory ideas. And a lot of times they'll draw two cars not like going by each other on the road, and they'll say they're not lined up properly. Well, that's not really right. That's like, or a baseball bat missing a baseball, but that's missing the first idea. That's showing that they have to collide. They have to collide up. They have to be lined up correctly. Would be more like, a head-on collision versus a T-bone collision, or when you're swinging your baseball bat if you hit like the ball on the handle, it's not gonna, be a good hit. Or if you hit the ball off the end of the bat, it's not going to go in the direction you want, or hit the bottom side of the bat, right? You have to line it up, but they still have to hit in order for that to be like a good, not good version, right? So that's not good because that's not the spots. I was trying to point at this thing, right? They're going to hit each other, but they're not going to hit each other, oriented properly. Here, they're going to hit each other oriented properly. So they have to hit each other. They have to be lined up right. There's a creepy little smiley face there for you, showing that works, right? They also have to have enough energy, right? So I've got a little analogy here. I don't know if we can, here, we'll tilt the screen so we can see my analogy. You see, I have a nice little wave out here, and I have a brick. So I think I could have a reaction, not a reaction, right? I could do a thing, right? I could do a thing where I like the brick lands on the weighboat, right? So there we go. Well, I'm going to have to hit it. I'm going to have to hit it lined up right? If I hit it this direction, that's not going to help. But I'm doing all these things right, but I'm not giving it enough energy. I've got to hit it with enough energy to tip the brick over, right? If I do this, it's not quite enough energy. So I've got to hit it with enough energy to crush the little weighboat. That's kind of satisfying. Oh, I might have to kill a couple hundred weighboats today. Just, it's really only the first one is really satisfying. After that, it's not so satisfying. Why wouldn't I have a brick in my classroom? I don't know why you're asking me that, right? So they have to have enough energy. When we talk energy with molecules, we're thinking speed. How fast are they going? If they're going really slow, then they're not going to be doing that, right? Now, remember, within one given temperature, some of them are going to be going faster and some of them are going slower. It's a distribution of speeds. So just because you're cold doesn't mean that none of them have enough energy, but not as many of them would have enough energy, right? Some practical examples of this, you might know, like if you put paper in the oven at home, it's not going to catch on fire if you put the oven at 200 degrees. But spontaneous combustion is a thing. What's paper in Fahrenheit? I think it's like 415 or something like that. And paper will spontaneously combust because then the oxygen has enough energy that it can react with the paper, but at a lower energy, it won't. Right? Kind of same thing with bumper cars, right? You keep bumper cars at a slow enough energy that they're not going to cause any damage. They can still collide, but they're not going to cause damage. Right? And the last idea is that they're going to form activated complexes. So when these things hit, they don't just magically happen all at once, right? They form this thing here, right? So this is not the reactants. We've seen the reactants. They're these things, right? They're not the products yet. They're like this transitional state between the reactants and the products, right? It's a transition state. Your reactants are not there anymore. Your products aren't there anymore. You've got this transitional thing in between. I like to use an example of a couple, right? I usually draw it on the board, but you've seen me draw. I don't need to bother with that, right? What you're supposed to do if you're dating someone in high school, which you shouldn't date seriously in high school, just hang out with your friends and stuff. But let's say you're dating somebody in high school and you've been going out for a little while and you decide, you know what, this person's boring. I don't enjoy hanging out with them. What you should do is you should say, thanks for spending time with me. I really enjoyed spending time with you. But I think it would be best if we did not spend time together anymore. Thank you very much. And I will see you later, right? Whatever. I don't know. I didn't get to break up with a lot of people because I'm me, right? So you do that. Then you wait an appropriate amount of time. I don't know, a year or something. And then you go to the person that you do like and you say, hi, I would be interested in possibly getting a cup of coffee with you sometime. You're in high school. You probably don't drink coffee. I would be interested in, you can't date because we're social distancing. I don't know, going on a virtual date or something for our example now. That's what you're supposed to do. Not everybody does the thing that they're supposed to do. Some people, like, I'm still dating this person, but I'm going to kind of start talking to this person and I'm going to maybe not text this person back right away. And I'll like start seeing if there's a connection over here, right? You're like kind of sliding over this direction a little bit. You should not do that. That's not classy, right? To do that, you should break up with one person and then but some people kind of start to feel out a new person and see, hey, does this person like me? And could I date this person? And then you like slowly sever tie, right? So that's this thing, right? Bromine is not so excited about hanging out with nitrogen and oxygen. Bromine wants to hang out with bromine. So we're in this high energy transition state. It's a high energy state. You can't stay there for long. right? You shouldn't ever get there in a dating situation, but you certainly chemicals can't stay there. You can't buy a complex, right? You can't go to the store and buy it. It's a temporary state. I stole a toy from my kids. I like this little toy because I was watching them play with it, and I'm like, that's like an activated complex. See, I have reactants that would be like this blue thing, and then I have products, which is this purple thing, right? But it has to transition from one of those to the other. So I'm going to point this upwards a little bit, and I don't know how well you can see the colors, but if we throw it in the air, see how when it's in the air, it like is wiggling back and forth, and it's not really either blue or purple. It's like both of those, right? So if I throw it up here, right, blue, can you see it when I'm catching it? Purple. See, like sometimes it goes back and doesn't react, sometimes it, right? But the transition state is like that thing in the middle, right? I've got a cool little demo that I'll do with that. I don't know what we're looking at time-wise, but I'll have to switch to a different video and stuff to do that. But anyway, that's our main ideas of collision theory. I think we get into reaction rates after this. Oh yeah, and then that's the products after you formed your activated complex. I think from here we go into reaction rate stuff. Yeah, so I think that'll do it for today. You should read the that section in the book, the 18.1. It will help reinforce these ideas. This is not mathematical that you can practice. This is idea stuff that you kind of got to get to know. When we're having face-to-face stuff, I spend a day having students draw pictures of this stuff because it's important stuff, and we want to understand it. Not just be able to say a couple of the words, but understand what it's telling us and stuff. All right. Talk to you later. Have a good day.